Okay, thank you all for coming. And I'm Hongyu Miao from University of Texas School of Public Health. So my research interests include time series, graphical model, and machine learning. And today I'm going to talk about network structure identification. Is that on? Yeah, I think it's on. Yes. Hello? There you go. Is that better? Okay. So nowadays, everybody is talking about data science, is talking about big data. So the curse of dimensionality is always a concern, okay, if you do the big data research. So this talk actually is about how to deal with the curse of dimensionality. I actually used the gene regulatory network as an example. Okay, we have been working on many different types of problems. Okay, and actually, network model or graphic model is one of my favorites. If we talk about the gene regulatory network, we're talking about like human genes. Okay, we know that the number of human genes is like 19,000. So if every gene is a node in a network and we want to understand the pairwise interaction between two genes, then we have actually a coefficient. So the total number of coefficient will be 19,000 by 19,000. So that's like 3.6 multiplied 10 to the power of 8. However, I will not be able to actually deal with this many parameters. Okay, I will explain why. Okay. So I will skip actually some biological background about the importance of the gene regulatory network. So I will jump to this plot. So nowadays, if you go to the literature, and you can find actually many plots like this. Okay. So here, if you see a dot, that's actually a network node. And if you see an edge here, that's actually a pairwise interaction. And here, these nodes are in different color, which means they're actually grouped into different communities or clusters, okay? So that's actually this kind of a structure we're actually trying to identify from data. And to be more specific, okay, so our model input is actually the time course gene expression level at each node or at each gene, okay? But in reality, okay, we usually only have like 6 to 10 time points. So the sample is really actually sparse. And the model output actually is the estimates of the edge coefficients. So they are zeros or non-zero. Zeros means the pairwise interactions does not exist. Okay. So there are actually many related work. Here I just list some of the representative work here. For example, people have think about use the information theory, clustering method, Boolean network, Bayesian method, state space model, regression model. Okay, people have tried many okay, different types of techniques to solve this problem. And some of them actually get quite popular. For example, the Pearson correlation or mutual information approach, they are very simple to understand and very simple to use. And also you have the ARCAN or CRR, Genie3, Tigris, that kind of techniques. They are actually based on different concepts and ideas, okay? There are some actually, a few methods are particularly for time course data. But actually the first one I listed here is actually an extension of the ARCAN method here. So this one, JUMP3, actually is an extension of the Genie3 algorithm. And the CTPR actually is from my group. And we start to actually work on this problem actually back to 3 years ago. And at that moment, we start to actually solve this curse of dimensionality problem. And we came up with a very complicated pipeline, okay? We did actually lots of things. We incorporated biological prior knowledge. We did the dimension reduction, and then we did the use the dynamic Bayesian network model combined with the constrained lasso method. And eventually, we can do resulting interpretation. Okay, so the highlight of this study is that we are able to use prior knowledge to reduce the number of parameters, okay, down to 0.37 million. Okay, so that's kind of the number of parameters we're trying to estimate. Okay, but in our simulation study, actually, we doubled the number of parameters. Okay, to even doubled and tripled. Okay, And so we actually can handle actually meaning parameters right now. So let's look at actually the performance, okay, of our first try. So this one actually is our algorithm, and ignore all the other criterion. Just look at the AUC, okay. If you look at this column, if the size of the network increases from 10 to 50 to 100, okay, and you see the AUC actually decreases from 0.96 to 0.57, okay. That's a kind of actually interesting and embarrassing observation because we aim to solve the curse of dimensionality problem, but we end up with improving the performance for the small size network. Okay. The bad news is that if you look at the performance of other algorithms, okay, they are even worse. Okay. So then we start to think about, okay, what we miss. Okay, that's actually the big question. So when we're dealing with this kind of question, we always have to consider sparsity, okay? So that's not something we're gonna drop from our model or method. Then actually after, days of discussion, okay, we think a hub structure could be the key to solve this problem. I will explain what is the hub structure, but I'm gonna explain why it works later, okay? So simply speaking, okay, if you look at this actually example, okay, small example, we have this small network, and if we actually also plot the adjacency matrix for this small network, you will see this, here, if you see a dot here, that's actually an edge. If you see white space, that means there's no edges. So if we do a simple linear decomposition, we just plot the outgoing edges associated with the hub nodes, okay? The hub nodes. So you will see a very clear column structure here, and what's left look like this. So that's actually very inspiring because if we think about lasso or SCAD, any kind of regularization technique, okay, the formalization is like what? You have a penalty coefficient in front of the sum of absolute value or parameter value, right? So lambda, sigma, theta I, okay? That's kind of the formulation here. But it does not incorporate any structure here. So it actually should only works for this kind of structure, okay? If you have this kind of sparsity structure, lasso will work perfectly. This actually has a very clear column structure. So actually lasso or SCAD, any kind of that kind of regularization technique will not apply. So then we start to think about the mathematical formulation, okay, how we actually do this. Here's some notation I'm gonna skip, given limited time, and we still use the dynamic Bayesian model. Basically, if we assume the Markov property and also make the Gaussian distribution assumption, okay, this dynamic Bayesian network model becomes actually a vector autoregressive model, which is actually straightforward. And then we just use this model, okay, to formulate a least square regression, okay, formulation. So that's this one. And we want to actually incorporate the hub gene structure, okay, into the formulation. And back to this slide, you will see that we have the original coefficient matrix C, and the column structure matrix actually is denoted by A, and here is the rest. That's a matrix B. So then you have C equals A plus B, okay, in the formulation. And we're going to handle A and B differently because B actually is suitable to be dealt with using the lasso technique. And this column structure actually has to be dealt with using the R21 norm regularization technique as suggested by Huang in 2010. And we also add some other constraints to make this more realistic, but you can ignore this part, okay? Because if you don't have this method still work fine. So also, we actually need to incorporate the prior knowledge, okay? So that's going to help us to significantly reduce the number of parameters. So here comes the actually final formulation. We have the least square term. We have the penalty for the column structure. We have the penalty for the rest of the sparsity structure subject to these constraints. And then we developed the optimization algorithm. Okay, this is not actually a brand new work. This is actually based on the ADMM approach. And we actually extended the ADMM optimization algorithm a little bit to actually make it run faster. Okay. Now let's look at the simulated data. Okay, we simulate the data using the dream challenge, okay, model. That's actually the kind of a gold standard here. And we actually also add, we doubled the number of edges or double the number of parameters, okay, when we generate simulated data because we need the structure noise. So we only consider 6 time points. That's actually a sparse sample. And actually, because in practice, most people actually use the average to do the model fitting. So that's the reason we generate only one observation at each time point to test our algorithm. Okay. So here are the evaluation criterion. But again, let's pay more attention to the AUC only. Okay. So here comes the results. The first one is still our algorithm, new algorithm. If you look at the AUC, okay, now we actually increase the network size from 10 to 100 to 1,000, okay? And you see that the AUC is actually stably above 0.8. So it works now, okay? If you actually look at the performance of all the other algorithms, okay, if you increase the network size to 1,000, okay, some of them actually drop to 0.36. Okay, that means that there are some actually systematic biases, okay, in the results. So actually our model, our method is the only one can be applied to a big complex network, like a network with 20K nodes. So here we did the additional simulation study. We increased the network size from 10 to 20K. And we also increased the measurement noise, okay, from 10% to 30%. And worst case, we still get AUC above 0.7. Okay, so that means our algorithm actually is quite stable against structure noise and measurement noise. So here's the application. Okay, actually, I need to actually go back to the slides to explain, okay, why this works. Okay, I just mentioned, okay, I used the hub structure, okay, and then solve the problem. Why? If you look at this plot, okay, you remember we actually divide the network into multiple communities, right? So what's the possible number of communities in a real large-scale complex network? Actually, you can find a very good Nature review paper, okay? People have done that for different types of networks, gene regulatory network, traffic network, social network. Actually, the number of communities will range from 50 to 200, okay? So basically, we want to use the model to reduce the dimension of the problem. So we actually start to think about how to model the communities, okay? But the topological structure of the communities are very complicated. So we cannot actually exactly model every community structure. That's the reason we think about the hub structure, okay? Instead of modeling every interactions within a community, we start to think about the center of the community, that's a hub, okay? Then once we can actually determine the hubs, or sequentially we determine the community structures, then we can reduce the number of the dimension of the problem, so we can get a problem solved. So that's actually the key idea here. And then after the simulation study, we applied the method to some real data sets. This data set actually is from influenza H1N1 virus infection data. And these are actually the gene expression pattern. This real data set only has 6 time points. And this is actually the overall network structure we get. And here is actually the largest hub structure we obtained from the analysis. And also we did some follow-up, validation. Okay, we compare actually the edge inferenced from data with the encode output, experimental validated output. So actually, for all the cases, okay, we have the highest accuracy. So in conclusion, our algorithm actually is novel and scalable, and it performs well for both for network data with both structural and measurement errors. And we have done extensive simulation study to actually verify the performance of the algorithm, and the success of this approach actually heavily depends on the incorporation of topological structure of networks. So this actually is a collaborative work with computer scientists, Dr. Jinyu, and also to Dr. Rice and Dr. Chen from Baylor. They helped a lot with the result interpretation. And also, we have some students helped with this project. And here's the funding support. And thank you, that's all. Yeah. OK, go ahead. Oops.
One more question. Sorry.
So my question is, how do you decide to divide the C into A plus B? So what's the threshold to decide if a certain column is A or B?
Actually, here we don't have a rigorous threshold, okay? Because that actually depends on definition of hubs, okay? So basically, if we rank the degrees of every node in a network, usually we choose a top 10% or top 20% node, okay, as a hubs. So that's actually empirical, okay? But in our algorithm, we didn't use a threshold for that. We just let the algorithm search for it.
Have you tried to tweak this number to get different results? For example, if you use 10 and 15, you probably get better or worse results.
No, like I said, in our algorithm, we didn't use that threshold. We let the algorithm automatically determine whether it's a hub or not. So we don't have that problem. Okay.
So we have time for one more question. All right, if we don't have any more questions, let's thank our speaker.
Okay, thank you.